Welcome and good morning. Myself G. Sivaraj, full-time research scholar, Department of Electrical and Electronics Engineering, Government College of Engineering, Salem. In today's session, we are going to see the MATLAB simulation of single-phase AC to DC fully controlled converter. In single-phase fully controlled converter, single-phase AC supply is converted into a regulated DC voltage, wherein the output voltage is controlled by adjusting the firing angle of the thyristors. Now let's see the aim. The aim is to simulate single-phase fully controlled converter with R and RL load for continuous conduction mode. Software used is MATLAB Simulink. Formula used is for average voltage 2 Vm cos alpha divided by pi, for average current V0 average divided by R, for RMS voltage Vm divided by root 2, where Vm is the peak voltage and Vs is the supply voltage, for RMS current V0 RMS divided by R. So before going into the simulation, let's get into the theoretical part. So thyristors S1, S2, S3 and S4 are used for the conversion process, and here load is the resistance. This is the input voltage waveform where Vs is the input supply and Vm is the peak voltage. Now let's see the operation. Initially thyristors S1 and S2 are triggered at an angle alpha, where alpha is the firing angle. So thyristors S1 and S2 will start conducting. At this juncture, thyristors S3 and S4 are reverse biased, so it will not conduct. The thyristors S1 and S2 will continue to conduct during the positive half cycle till pi radians. After pi radians, the thyristors S1 and S2 will be reverse biased because of the negative voltage being applied across S1 and S2. At angle pi plus alpha radians, the thyristors S3 and S4 are triggered, and this will start conducting. So when these thyristors are triggered in this fashion, we'll get the output voltage waveform like this. Now let's see the operation of the single phase fully controlled converter with RL load. Here the additional inductance is added in the load side. Here also the thyristors S1 and S2 are triggered at an angle alpha. So the thyristors S1 and S2 will be conducting during the positive half cycle. At pi radians, since the load current will be continuing to flow through the load because of the inductance, the thyristors S1 and S2 will not stop conducting. It will continue to conduct till pi plus alpha angles. At pi plus alpha angle, when the thyristors S1 and S2 are triggered, this will start conducting. So the thyristors S1 and S2 will stop conducting. So when the thyristors are triggered in this fashion, we will get the output voltage waveform like this. So this is the tabulation chart for the R load. When firing angles are changed, we can measure the output parameters, and this output parameters can be compared with the theoretical value. For RL load also, the output parameters can be measured for different firing angles, and these values can be compared with the theoretical value. So this is the opening page of the MATLAB Simulink software. So this is how the opening page will be looking like. So now we need the blank workspace for drawing the schematic and doing the simulation. So now we will click the Simulink tab here. So once it is selected, we can have different blocks here. So we will click the blank model. So once this is come, so let us save this into a folder. We can give any name we like. Let us give it as sample. Let's save it. So now we need the file is saved as a sample, and these are all the parameters that we need for the simulation. So this is the input AC voltage source, and this is the linear transformer which is required for stepping up or stepping down the AC voltage, and this is the thyristor switch which is going to do the or conversion process, and this is the pulse generator block which is used for giving the firing pulse to the thyristor, and this is the voltage measurement block, which is used for measuring the voltage output, and this is the main block, which is used for converting the instantaneous DC voltage into a average voltage, and this is the RMS block, which is used for converting the instantaneous AC voltage into RMS voltage, and this is the series RLC branch, which can be used for creating any resistor, capacitor, or inductor, or the combination of any of these. And this is the mux, and this is the scope block, which is used for seeing the waveform, which will be used as a CRO in our practical lab, and this is the display for viewing the instantaneous voltages or any parameter, and this is the power GUI block, which is essential for running the simulation. So now let's see how to select the components. So we need to click the library browser. So here we can get all the components that we need here. For selecting AC voltage source, either we can type in the search box and select the components, or we can go directly into Simscape, Power Systems, Specialized Technology, and Electrical Sources. So here we can click the AC voltage source, right click it, and add block to model sample. So if we click this will get added to our workspace. The similar way, if you need a linear transformer here, we can type in it as linear transformer here. Once it is entered, the linear transformer will be visible. So this can be right clicked and added to the model. So then we need thyristor. So we can type in as thyristor. So thyristor block is available, so this we can add it. Next we need a pulse generator. So we can click in as pulse generator, or we can go to the sources. We can find pulse generator here, we can add it. Then voltage measurement block. So voltage measurement block is available, so this also we can add it by doing a right click. Next we need mean and RMS block. So the block which is available in the DSP system toolbox or any other stuff, we need not it need not to be selected. So those blocks will not work in our Simulink model. The block which is available in the Simscape, so that need to be selected. So here we can click the RMS block and add it, and mean block also we can add it. So we need a series RLC branch for connecting the resistance load. So we can type in as series RLC branch. So there are two things named as series RLC branch and series RLC load. So for our circuit connection we need series RLC branch only. We can right click it and add it. Then we need a scope and a display. Scope which is available in the Simulink library, we can add it. Display which is available in the Simulink can be added. Next power GUI. So this also we can add it. Next, mux which is available in the Simulink library can be added. So with all the parameters or blocks selected, so we need to give the connections. The connection for all the parameters are given as shown here. Now let's see the parameters of the block one by one. And this is the AC input voltage source. Here we will have to double click in, and the parameters need to be selected. This is the peak amplitude. So we need to give 230 volts input. However, the RMS input cannot be given here. Only the peak amplitude can be given. So 230 volts need to be converted into peak amplitude. By multiplying 230 volts with root 2, we'll get 325 volts. The input supply frequency is 50 Hz. The value can be given here. So if you need to measure the 230 volts input, and if you want to see it, we can give the voltage measurement block here. So this can be measured using the voltage measurement block. The output of the voltage measurement block can be given to the RMS block. So the RMS block parameters are for the fundamental frequency. If there is any other frequency other than 50 Hz, this need to be changed. So this can be set as 50 Hz. If there is any other initial RMS value, that need to be changed to 0 volts. The output of the RMS block is given to the display block. So this is for viewing the output voltage. Next is the linear transformer. The parameters can be selected like this. So for units, we need to have SI units, and this is the nominal power and frequency parameter. So we need to give two parameter values, power and frequency. For the power, for our application, we can give us 1000 watts, and frequency can be set as 50 Hz. And since this is a single phase transformer, we need to give the two winding parameters. If there is a three phase transformer, we need to select this third winding parameter also. Since this is not applicable here, we are unticking it. So the first winding parameter can be set according to our input voltage. Since we are giving 230 volts input, we can give the voltage parameter as 230, and resistance and inductance of the winding parameter can be set as 0. And for the winding 2 parameter, for instance, in our case, we will give the 24 volts input to our rectifier circuit. So the voltage parameter can be set as 24, and resistance and inductance of the winding 2 parameter can be set as 0. So after setting it, we can give apply. So these other parameters can be left as default values. So if you want to measure the input supply which is going to be applied across our rectifier circuit, we can connect the voltage measurement block, and it can be measured. So this measurement block output can be connected to the RMS block, and this RMS value can be measured in here. The 4 thyristors need to be selected like this. If suppose we want one more thyristor, we can right click the thyristor block and drag it. So the one more block will be created. So like this, we can select any number of, we can have any number of thyristors or blocks for us. So next is the pulse generator block. For pulse generator, this is the block which is going to decide the firing angle of the thyristors. So the block parameters can be set like this. So the amplitude can be any, it can be 1, 2 or any other value. So this is not going to change our firing pulse amplitude. Period, since we are going to operate with 50 Hz frequency, the period can be given as 1 by 50 or 0.02. Pulse width, here a small pulse can be given, so we can give 5 or 10 whatever value we want to give. So this is not going to make any difference. So now for instance we will give 5 as the pulse width here, and phase delay. For setting the phase delay parameter, we need to do the calculation. For input supply frequency 50 Hz, the time period will be 0.02 seconds, and for firing angle, so we need to do the calculation as shown here. 0.02 seconds is the complete time period of one cycle. So for one cycle the angle will be 360 degree. For 30 degree angle, the after doing calculation we will get 0.0016 as the value. This 0.0016 can be given as the phase delay in our pulse generator block for firing angle 30 degree, and for pi plus 30 degree, that is for the firing angle which is need to be given to the thyristors S3 and S4. It shall be pi degree away from our firing angle of the thyristor S1 and S2. For instance, for 30 degree firing angle of S1 and S2, firing angle of S3 and S4 will be 210 degree. So by doing calculation we will get the phase delay value as 0.0116 seconds as the value. So now the value is entered here. So this 0.0016 is given for thyristors S1 and S2, and for thyristors S3 and S4 pulses are given for firing angle. Pulses are given for firing angle. Pulses are given for 4 thyristors. Pulses are given for 4 thyristors, and now we will see the thyristor parameters or SCR parameters. Here we can have the default values. This is not going to do any change in our simulation. Resistance can be set as 0.001 itself, and forward voltage can be given as 0.8 volts itself, and we need not to change these number parameters. And next is the load resistance block. For our application, let us have 10 ohms as the resistance value, and this is the voltage measurement block for measuring the voltage output. This voltage output can be given to the main block for average voltage measurement and given to display for the display purpose, or we can give this output to the RMS block also for measuring the RMS output voltage measurement, and this output can be given to the scope also for viewing in the scope. Here in the RMS block the parameters need to be set. Here the fundamental frequency need to be set as 50 Hz because we are operating with a 50 Hz input supply. If suppose this is having some other value, this need to be changed to 50 Hz, and main block parameter also need to be set as 50 Hz only. And next is the scope. For instance, now we will have to select the configuration parameters. If suppose in the logging tab, if the limit data points to last are enabled, this need to be disabled because we need to view the whole simulation. After setting it, give it as OK. And next is the Power GUI. The simulation type can be set as discrete for our application, for our simulation purpose, and this sample time can be kept as default value. And this is the configuration parameter setting. Here solver selection can be selected as variable step, and OD23 TB stiff TR BDF F2. Once this is set, now we can start running the simulation. So here we can view the 230 volts input, 230 volts RMS input. We can see 24 volts output we are getting from the linear transformer. Now the simulation is running. So now the simulation is done. Here we can see the average voltage, average output voltage value, and we are seeing the RMS output voltage value. If we double click the scope, we can see the complete simulation output. So if we want to see the closer values, we can select like this by selecting this dragging button. So this is the input voltage which is given to the thyristors. 24 volts input we are giving here, and this is the output voltage what we are getting it from the single phase rectifier. So here we can clearly see at 30° alpha angle the SES are triggered in, and this is the output average output voltage value. So here we can see both input and output voltage values. The average voltage that we are getting it as 18.93 for the input RMS voltage 24 volts. Now let's compare this simulated value with the theoretical value. So input voltage is 24 volts. So the output voltage calculation is 2 Vm cos alpha divided by pi. For 24 volts input, the peak output peak voltage will be 33.936. By multiplying 24 volts into 1.414, we will get 33.936. So by doing the calculation using this formula, we can get the output voltage value. Now let's verify the value. We know Vm is 33.936. This can be multiplied with 2, and for cos alpha, that is cos 30°, the value is 0.866. This need to be divided with pi value, that is 3.14. We are getting 8.7 volts. So the theoretical value and the simulated values are matching. That's all as far as simulation of a single phase fully controlled converter is concerned. Thanks for watching.